So now that we've discussed definite integrals, we need to talk about indefinite integrals. And if you go back and watch the video about antiderivatives, it kind of touches on that, but now we're going to discuss indefinite integrals as opposed to definite integrals. So basically what we want to have is we want to have a nice notation. So if you remember back to calculus, we had really nice notation for what it meant to evaluate the derivative. So we had, d dx, and that meant find the derivative of the following. So we need to know, some sort of notation to mean find the antiderivative of the following. And the way we do that is an indefinite integral. And what an indefinite integral is it's an integral or an integrand with no bounds. You do need to have the integrand and then also a d something to tell you what the variable is. Just like with derivatives, we had to have d something on the bottom to tell you what the derivative was. And what this means is that we're taking the antiderivative of the smaller function, and it's going to equal the larger function, capital F of x. So you want to be careful. A definite integral, so one that has bounds, the answer is going to be a number because it's talking about the area under a curve, it should be a number. Whereas an indefinite integral, so one that doesn't have bounds, that should be a function or some sort of family of function, up to a constant, but that's talking about a function, not a number. So definite integral, your answer should be a number. Indefinite integral, your answer should be some sort of function. The connection between the two, as we know, is that if you're looking for a definite integral, so one that has bounds, you should find an antiderivative and then evaluate it from a to b. So let's just do a little bit here. So if f is an antiderivative of the smaller function f, then the most general antiderivative is going to be plus c. And the reason is because if you remember, for an antiderivative, you take the derivative to get back to that original function. Well, taking the derivative of a constant is 0, so that's why you should include all of these plus c's for antiderivatives. So if I'm looking at, let's say, the antiderivative, ignore that 0, the antiderivative of 1 over x dx, then I'm thinking, think of a function whose derivative is 1 over x. Because I think derivatives are easier to think about than antiderivatives. So I'm thinking of a function where when I take the derivative, I get 1 over x. And the answer to that is natural log, and we have to use absolute values of x because you can't plug in negative values to the natural log. But then because this is a general family of functions, I need to include this plus c on the end. So another example here, the antiderivative of secant squared x. So I'm doing the integral, so integral of secant squared x dx. I'm thinking in my head, what's a function that you know whose derivative is secant squared? So the derivative would be secant squared, that means my function would be tangent. But because we're looking at a family of functions, my antiderivative, so my indefinite integral, will give me tangent x plus c. And here is just a list of antiderivatives that you should know. All of these are based on what you learned in calculus. If you added two functions, their derivatives, you just add. Same thing with antiderivatives. We have the power rule. So this one here, you want to be careful. If n is equal to -1, that's 1 over x. And if it's a 1 over x, you have to take into account the natural log. And you can just read through these, but the idea is if you take the derivative of whatever function is on the right hand of the equal sign, you better get what was on the inside of the integrand. So let's look at one example. So 10x to the 4th minus 2 secant squared x. So I'm thinking of a function whose derivative is 10x to the 4th, and then a function whose derivative is -2 secant squared. So I'm going to use the properties that we just dealt with. The first one is I can break up this integral. So I can break it up to be this integral minus this integral. But then also we can bring constants out front. I think my computer just freaked out for a minute. I apologize. So we're thinking of breaking this up, also bringing out the constants. So I'm going to bring out the 10, but then I'm also going to bring out that 2. So that's what I did here on that first line if you're looking at it. So I brought out the 10, and then I also brought out the 2. From there, I use the power rule. My computer's just not having it today. I'm going to use the power rule on that x to the 4th. So x to the 4th, the antiderivative, you add 1 to your exponent, divide by your new exponent, so that'll give me x to the 5th divided by 5. We've already talked about this one before. Antiderivative of secant squared is tangent, so that's where I got the tangent. And then just do a little bit of algebra, clean it up a little bit. 10 over 5 is 2. So I get this answer. Now you can always double check your answer. So let me show you how you always double check your answer. The way I can do that is let's take the derivative. Over here. Let's do the derivative of 2x to the 5th minus 2 tangent x plus c. So the derivative. So the derivative of 2x to the 5th, that would bring down my 5, get a 10. So 10x to the 4th. Minus, and then I'll keep that 2. Derivative of tangent is secant squared. And the derivative of any number is 0, so that's my final answer. And what you notice is that this was inside the integral in the very beginning, so I know that I've done this problem right.